Hello, this is Dr. John, your physics and math professor, coming to you with another pulley problem. Here we have a pulley, a weight hanging from a pulley of 10 kilograms, and we have another weight on an incline, 30-degree incline, mass number 2, 5 kilograms. We want to find two things. It's pretty common for pulley problems. One is the tension in this pulley. If you remember from before, the tension in the pulley stays the same here and here. All the pulley does is redirect the force, redirect the tension. That's all it does. And we have one acceleration for the system. This rope stays taut like this, so the acceleration will either be in this direction or in this direction. So one of the first things that I tell you to do for this, number one, is assume a direction for acceleration. In these kinds of problems, and practically all these problems, assuming you don't have some sort of friction here, if you assume a direction for acceleration and get it wrong, your acceleration will be negative in the end. And you know you've gone the wrong way and you have to go the other way. But in almost all the problems you're going to be able to know what the acceleration would be. So in this case, look here, there's a 10 kilogram mass here. This is a 5 kilogram mass. You know that the force that this thing pulls at is going to be reduced by the fact that it's on an incline. How do you know that? Because as the incline gets flatter and flatter, this becomes less than 30 degrees, say 10 degrees or 5 degrees, it's going to pull very little in this direction. As it gets higher, closer to 90 degrees, it's going to pull much more like you just have straight up two weights on a pulley. Then this is going to be important. But the most this could pull by is 5 kilograms times g. This is always going to pull more. So what do we know about the acceleration? We know for sure it's going to be in this direction. So we know we can assume the acceleration is in that direction. We do everything else in accordance with that. Now we're going to isolate each of the masses, and we'll draw little isolation boxes around them like this. I'm going to redraw box number 1 here. All right, here we have our isolation box drawn around mass number 1, and we want to use Newton's law. Newton's law is very straightforward, that the net force, the total force, the unbalanced forces acting on an object are going to be equal to that object mass times acceleration. Here we have this specific mass, so it would be mass 1 times acceleration. What are all the different forces acting on this? Well, we have, for one, we have this tension pulling upward. There's only one tension, so we'll just call it T. And we have this going downward, which would be M1G. M1, make sure that you choose the right mass for each of these. Now, if you want to say, what is the acceleration of this box here? Well, the mass, 1, times the acceleration is the same for both these boxes, is equal to what? We know it's accelerating downward, so this is going to be bigger. M1G minus tension. Here we have the first of the two equations we're going to need, because we're going to have two unknowns, the tension and the acceleration. I'm going to write that equation over here and then double check. M1A, M1G, tension, minus sign. Make sure you have everything correctly labeled. Now we can erase this side, and I'm going to isolate this one. It's a little harder now because we have an incline. So here we have M2. I could draw this isolation box around M2 just like I did here, but you can sort of see it right over here. I think I don't need to do that in this case. So let's take a look at this and see what forces are acting on this one. I can draw this all out, and then I'm going to do an exercise with it that will hopefully make the problem easier for you. First of all, we have this force. This is an obvious one. That's the tension acting straight up the incline here. That's the same tension over here. And then we have this force acting this way, which is M2G. And if we wanted to think about this for a second, it's acting at an angle here. What is this angle? What would this angle up here be? Well, if you take this angle theta here, if you flatten this out, you made this less, what would become this angle here? This angle up here, alpha. Notice as you flatten this out, this would squeeze together as well, so the angle alpha is the same as the angle theta. So we wouldn't need to write alpha in there, we can just write theta and it's the same angle. So that's the angle, that's mg acting downward, and it's of course going to have two components. Now you can keep it like this and work on it like this. Some teachers like to do that. I find it simpler to be able to take this whole thing and sort of flatten it out. I'm going to, right down here, I'm going to take the same thing and flatten it out. That is, look at it as if your head is tilted and you're looking at it at an angle here. So here I have flattened this box out, M2 out, and I still have the tension acting in this direction. That would now be a straight horizontal force. And now I have this dashed line, which is like the normal. It's at 90 degrees to the surface, so I'm just drawing it like this. And I have this force acting here, which is M2G. That's this force acting here. It's acting at an angle of theta degrees. Now what can we do? We can break this into components. Let's do that with different colors so that it's easier to stand out. So we have this component right here. we've hopefully done this for a number of different problems. I'm going to blow this up here. Here you have this downward thing, you have this thing here, and you have this. This is mg. This is the original, this is mg up here. This is mg, this is the angle theta. What is this value here? So we know that the sine of theta is equal to x over mg. X over mg. The opposite over the hypotenuse, which means x is equal to, move this over there, mg sine theta. So this component right here, this blue component, which is going to pull this in this direction. You always move vectors around as long as you keep their direction and their length the same. So this thing over here is the same as the force pulling in this direction, which is going to be equal to m2g sine theta. Now we also have a component acting downward here, this way. This component here, which is acting straight down to the surface. But we're not concerned about that because we don't have any friction. We would be concerned about that if we wanted to create a normal force going upward, but we're not. We only are concerned about this force over here. So right now I can erase this, and I can erase this, and we can work on writing another equation, a second equation here. All right, I'm going to use my tiny little diagram down here to create an acceleration equation for m2. First of all, we have to use m2 times acceleration. That's the mass times the acceleration is going to be equal to what? We know it's accelerating this way, so the tension is the bigger force. So it's going to be equal to the tension minus this, m2g sine theta. Those of you who are jumping ahead of me realize we're using 30 degrees. Sine theta is 1/2. You could plug that in right away. I'm leaving it for now though, so that you can see the final result, how it is very analogous to what we get for other pulley problems as well. So now we can take this. We don't need this diagram down here anymore because we have one equation there. We have a second equation here. I've taken this equation, I've left it up here, and I've also written it down here just so we have it for reference for later in case we need it. Now here's equation 2, here's equation 1. We want to be able to eliminate something so we can solve for either the acceleration or the tension. Let me take equation 1 and rewrite it up here as well. Here's equation 1 from here. m1a is equal to m1g minus tension. Now what we can often do with these is we'll take equation 1 and 2 and add them to each other, or subtract them, or divide them, or multiply them, or we would solve for something. Let's say we wanted to solve for t, plug it in here. You could do that as well. The simplest way to do this one here is to take these and add them up, because if this is equal to this and these two are equal, you can always add an equal thing to both sides of an equation. So we're going to take this and add this, take this side and add this. Why? The t is positive, here it's negative. So those two t's are going to add up and become 0. So let's add that up right here with a bright red. This plus this. You notice it's m1a plus m2a. So can I do this right away? Is that jumping too far? So it's m1 plus m2a here is equal to, the t's cancel because there's a plus t and a minus t, and then we have this. We have m1g minus m2g sine theta. All right, we have the makings of something. We have m1 plus m2. Let's move that over to this side. Divide both sides by m1 plus m2. We have something here that has g in it. We could take the g out for each of these if we wanted to. I will do that, but I'm going to erase this just to give myself some room to do that. So I'm going to rewrite this whole thing now. This is canceled here. A is equal to, remember we canceled this when we moved it over to here. We have a g for each of these. So it's going to be m1 minus m minus m2 sine theta all times g, all divided by m1 plus m2. There we go. We've got a beautiful, one big beautiful equation. And here we have on the bottom, again, just like before, on the bottom we have the net inertia of the system. Both these masses have to be pulled by whatever force is pulling them. On the top we have the net force that's acting in this direction. M1g would be this force. This force is it's reduced by this component, which is where we get the sine theta multiplied by m2. It's a reduction in the total impact of m2 because you're on the incline. And of course, it depends on the angle. So now you would have a universal equation for this. You can punch in the answer anytime for theta. You can punch in the masses. We'll do that now as we try to calculate the acceleration. So the acceleration is equal to m1. This is m1. Let's not confuse them. It's going to be 10 minus m2 is 5. Sine of 30 degrees is 1/2. This is multiplied together, times 9.8, all divided by 15. I don't know if you could do that in your head or not. This 5 times 1/2 is 2.5. 2.5. 10 minus 2.5 is 7.5. So let's just do that here. 7.5. Can I write that in here without making a big mess? 7.5 times 9.8. There, I hope I didn't confuse you by doing that all like that in my head. Now we have this is about half of this, so this is 2 in the bottom. 9 divided by 2 is about 4. Let's check my calculator and see what I get for the acceleration. So when I punched it into my calculator, I got 4.9 for the acceleration. I can write that up here. So the acceleration is 4.9 meters per second squared. So this thing's accelerating that way. This thing's accelerating that way. That's about half of gravity of what normally you would be doing with gravity, and it's because of the resistance of this thing. So now we found the acceleration of the system, we can find the tension. We have an equation for tension here and here. This one looks like it's easier. We're going to take this thing, I'm going to rewrite it. M1A is equal to M1G minus tension. So how about if we take the tension to this side and take this to this side, this to this side? Is that too confusing? That's going to be equal to M1G, and then this is going to be minus M1A. So this on this side becomes minus, this becomes plus. Hope that wasn't too many steps at once. I can take the M1 out of here, M1G minus A. There's sort of a tension equation. Let's see if it makes sense. The tension would be equal to M1G. If you were just holding on to this here and it wasn't allowed to accelerate, the tension would be equal to M1G. The tension would be the same as M1G, which is the downward force of this mass and gravity. But because it's accelerating, it's being reduced by this amount. If you were in free fall, then it would be reduced by the acceleration. There would be no tension at all because the acceleration would be equal to G. So it would just be M times 0. That sort of makes sense. Nice to have an equation that sort of makes sense. Plugging in the numbers, let's see if those make sense, is 10 times 9.8 minus, what do we have? 4.9. This is about 5. 10 minus 5 is about 5, so it's about 50. I'm actually getting 49 newtons. Awfully close on the estimation. I would do this regularly, unless the numbers are massive or really difficult. I would do a quick in your head, wild calculation, see if you're even close. That helps you to avoid silly math mistakes. So this tension here is 49 newtons. So there we go. We've done this slightly more complicated problem. If this helps, like and subscribe, and check out my next video where we're going to continue to do more and more complex problems with pulleys. And hopefully by the time you've walked through this, you'll have a pretty good idea of how to do this yourself. I will see you later. Bye-bye.